You type 6 words into ChatGPT, "Why is the sky so blue?" Then you press send. Almost immediately, text starts appearing. It feels as if your question went straight into one giant brain and the answer came back. But that is not what happened. Before the first word appeared, your request may have crossed an edge gateway, a routing system, a context builder, a tokenizer, a safety layer, a scheduling queue, a cache, and a cluster of accelerators. And if the answer needed current information, the model may have left its own generation loop, called another tool, received the result, and started thinking again. So let us follow one prompt through the entire machine. One important note: OpenAI does not publish a complete map of ChatGPT's private production infrastructure. So the network, regional routing, queue, and batching layers in this video are a simplified engineering model of how a system at this scale is typically built. The pieces we can verify publicly are still enough to tell the real story. ChatGPT can assemble conversation state and relevant memories, route between different kinds of models, break text into tokens, reuse prompt computations, call tools and stream output as it is generated. Here is our map. 9 stages. We begin in your browser. When you press send, the browser does not transmit only the sentence you typed. The client packages a structured request. It needs your new message, a reference to the conversation, the selected mode or model, any uploaded files, and the product capabilities available in that chat. It may also carry settings that affect the response. The request travels over an encrypted connection. Network systems guide it toward a service edge that can accept it. At this point, no transformer has answered anything. The system is still identifying the session, validating the request, and deciding where this piece of work belongs. Think of it like arriving at an international airport. You are inside the building, but you are nowhere near your gate. At the service edge, the platform can verify your session, enforce usage limits, and apply protections against abuse. Then, a router decides which execution path should handle the request. That does not always mean the same model. OpenAI has publicly described ChatGPT systems that use routing to choose between faster chat behavior and deeper reasoning behavior based on the conversation. A user-selected mode can also influence the path. Capacity matters too. Large AI services have to distribute work across available infrastructure. The exact regional and load balancing design is private, but the goal is familiar. Send the request to healthy capacity without making the user wait longer than necessary. Now, the request has a destination, but it is still missing most of the information the model will actually see. This is one of the most misunderstood parts of ChatGPT. The text you type is not necessarily the entire input to the model. A context-building layer assembles the information needed for this turn. First, come high-priority instructions that define how the assistant should behave. Then there is your current message and relevant content from the conversation. If you uploaded a document, selected excerpts or representations of that file may be added. If tools are available, the model needs descriptions of those tools so it knows what it is allowed to call. Personalization can add another layer. OpenAI says that when memory and reference chat history are enabled, relevant information from previous conversations may be added to new chats. The keyword is relevant. ChatGPT is not simply dumping every conversation you have ever had into every request. All of this must fit inside a finite context window. A real product, therefore, has to decide what to include, what to compress, and what to leave out. OpenAI does not disclose every selection rule used by ChatGPT, so treat that part as product logic, not a single universal algorithm. By the time context assembly finishes, your 6-word question may be sitting inside a much larger structured input. Before and around generation, the platform can use classifiers, rules, and policy checks to identify risky requests or outputs. Do not picture one magical red filter. Modern AI safety is layered, and different checks can happen at different points. The text is also converted into tokens, the units the model actually processes. A token can be a whole short word, part of a word, punctuation, or even a space pattern. In English, one token is often around 4 characters, but that is only a rough rule, and it varies by language and content. Each token becomes an integer ID. Those IDs are mapped into vectors, numerical representations the neural network can process. The model does not receive a paragraph in the human sense. It receives an ordered sequence of numbers that preserve enough structure for the network to work with language. Now we reach the expensive part, model computation. Your request may wait briefly for accelerator capacity. High-throughput inference systems commonly schedule and batch work, so expensive hardware stays busy. OpenAI does not publish ChatGPT's exact scheduler, so the boxes here are illustrative. But OpenAI does publicly document prompt caching. When requests share the same prompt prefix, the system can route them toward servers that recently processed that prefix and reuse intermediate computations. The technical object often discussed here is a KV cache, short for key value cache. During attention, the model produces key and value tensors for prior tokens. Saving those tensors means it does not need to recompute the entire prefix for every new generation step. This is not the same as ChatGPT memory. Memory stores useful information that may personalize future conversations. A KV cache stores temporary numerical state that accelerates inference. One is product context, the other is computational reuse. The prepared tokens enter the language model. Each token starts as a vector. Inside the transformer, attention lets every position weigh information from other relevant positions. In the sentence "she sat by the riverbank," the word river pushes bank toward the meaning of land beside water, not a financial institution. That transformation happens across many learned layers. The exact architecture and serving layout of the proprietary ChatGPT model are not public, and we should not pretend otherwise. What matters is the output of the pass, a score for possible next tokens. Suppose the visible context ends with "the capital of France is." The model might assign a very high score to Paris, smaller scores to alternatives, and tiny scores to thousands of other tokens. A decoding strategy selects the next token. Then the loop repeats. The selected token is appended to the context. The model computes scores for the token after that. Then the next one, and the next one. This is why the answer can stream. It is not created as a finished paragraph and then revealed with a typing animation. It is generated sequentially. Reasoning models can also use additional reasoning tokens for internal computation before or between visible outputs and tool calls. Those internal steps do not need to be shown to the user for the final answer to benefit from them. One model response is therefore not a single database lookup. It is a repeated prediction process running across specialized hardware, with previous computations reused wherever possible. Sometimes the model cannot finish from its existing context. Ask for today's weather, the contents of a file or an action inside a connected application, and the model may need a tool. Instead of generating the final sentence, it produces a structured tool call, which tool to use and the arguments that tool needs. An orchestration layer validates the request, executes the tool, and returns the result. That result becomes new context for the model. Generation resumes with information it did not have before. The loop can happen more than once. Search, inspect a source, calculate something, then write the answer. The language model is deciding what information or action is needed, while deterministic systems perform the actual retrieval or operation. This also explains why tool-based answers can take longer. You are no longer waiting for only token generation. You are waiting for external systems, network calls, file processing, or code execution, followed by another model pass. As visible output tokens are generated, the server can stream partial events back to the client. OpenAI documents streaming responses over server-sent events, and persistent modes can also use a WebSocket connection. That is why the first words can appear before the final paragraph exists. The delay before the first word is called time to first token. It includes work such as routing, context preparation, queuing, prompt processing, and any initial reasoning. After that, generation speed determines how quickly the rest of the answer arrives. The browser receives small response events and updates the conversation view. Markdown becomes headings, lists, or code blocks. Citations and tool status can be rendered as structured interface elements rather than plain text. Before or while content is shown, additional safety and presentation logic can affect the output. The completed interaction can then become part of the conversation state, so the next turn has continuity. That does not mean every chat is used in exactly the same way. ChatGPT has separate controls for history, memory, and model improvement. OpenAI says users can turn off Improve the Model for everyone. Temporary chats are not saved to history, do not create memories, and are deleted from OpenAI systems after 30 days, although they may be reviewed for abuse monitoring. So the lifecycle of your message depends not only on model inference, but also on the product mode and your data control settings. Now, the latency mystery is easier to solve. A long input can increase prompt processing time. A cache-friendly repeated prefix can reduce it. A busy service can add queue time. Deeper reasoning can delay the first visible token. A long answer adds decode time. A tool call can add an entirely separate network and processing loop. That gives us 4 useful myths to remove. Myth 1. ChatGPT searches the internet for every answer. It does not. Search is a tool used when the product or model decides it is needed or when you explicitly request it. Myth 2. The model reads your entire account history on every prompt. Relevant history or memory may be added when those features are enabled. That is different from copying every old chat into the context. Myth 3. KV cache is long-term memory. It is not. It is numerical inference state used to avoid repeated computation. Myth 4. The answer is written first and animated later. In a streamed response, output is generated and delivered incrementally. Once you separate context, computation, tools, and product state, ChatGPT stops looking like one magic box. So what happens after you press send? The client packages your request. Edge systems accept and route it. A context builder assembles the instructions and relevant information. The text becomes tokens. The work is scheduled, with cached computation reused when possible. The model predicts 1 token at a time. It may call tools and resume. Partial output streams back to your screen, and the interaction becomes part of the product's conversation state according to your settings. One ordinary prompt touched an entire distributed AI system before the answer felt instant. If you want the next layer, comment with one word, cache, tools, or GPU. I will turn the winner into the next visual breakdown.